And we're going to be talking about Chapter 6, and it's going to be on developing fundamental PLC wiring diagrams and ladder logic programs. And here we're going to talk about electromagnetic control relays. This section here, we're going to talk about PLC was originally designed to replace control relays that made logic decisions. An electrical relay is a magnetic switch which uses electromagnetism to switch the contacts in a relay. Now here is a normal relay. This is basically a de-energized control relay. Normally they'll have two to four contacts in there. Two of them will be normally open, two of them will be normally closed. In the de-energized state, when they're energized, when the coil is energized and it pulls these contacts down, the contacts that were normally open would now normally close, and the contacts that were normally closed would open. Okay. Now here we have the symbols here. This is a normally closed symbol in the ladder logic, and this is normally open. And then this is the physical relays within the contacts within the relays. So here you're seeing the normally open and the normally closed. And then over here, once the coil is energized, you see that those normally open are now closed, and the normally closed contacts are open now. And that's on the energized state of that relay. Now you have a motor relay here that they'll start motors, and they can actually work on three-phase or 220 circuits, and they can be energized for 24 volts AC or DC. And this is a symbol, and then this is the actual coil within that relay, and these are the contacts that are in the relays. Some of them have 6 contacts. Some of them, they're bigger relays will have more contacts if they need them. But anyway, they'll be showed with an M next to them in a ladder logic diagram now. We're talking about ladder logic, okay? And then control relay is used for controls. They're actually smaller things to turn light bulbs on, things like that, at lower voltage. And here again, this is a symbol for the relays that are contained in that control relay. And there's the coil that energizes, and then it either changes the state of this to open, because in a de-energized state, this is normally closed. So when you energize the coil, this one would open. You have to think of that because when you're going to start dealing with the PLCs, you got to understand what these relays and these control devices that you're controlling do, so then you can see where you place them. You're going to let the PLC make the decisions for you. Now here's a ladder logic diagram. You have a start switch or a switch that's normally open, okay, and he controls the relay, the coil that's within that relay, that control relay. And here you have 2 sets of contacts that are inside this relay, those ones we looked at on the last slide. Okay, in this state right now, with the start, with the S button, I assume that's start, open, you're going to have the normally closed relay contacts providing power to the green light. Okay, once you energize that coil by hitting this switch here, it's going to energize the coil, it's going to de-energize this relay and activate this relay. So in other words, you're going to start letting voltage run through this ladder in the ladder diagram, and the voltage stops flowing here because this relay becomes open and this one becomes closed. Now here's the same circuit built in in RS Logic, and you can see where there's your control over there, and then these are your relays, and you see they're kind of a little different, but we'll get into that a little bit later. Now we're going to get into contactors. This is section 6.2. Now these are the heavy duty motor control and pump and that pull a lot of circuitry. These will pull 3-phase, they'll do 3-phase type circuits. Now here you can see how they are. They basically push when they energize, these contacts go over here, and see you have your input line side, and then you have your voltage that's on here. So you have connections on these points and these 3 points here. These are your line sides, and this is your load side. So essentially, your pump or your motor connectors would go here. Then your voltage from your power distribution system would be going in here. You'd have 3 black leads going in here, and then you'd have your red, black, and green or yellow wires connected here, which would go to your pump motor or whatever you're trying to energize. So once you energize this coil right here, these relays here, they're normally open, they're all close. And mechanically, they're going to go, you see these little contacts here, it takes the line in, and then it puts that out to the pole, to the motor. So you can see where the contacts are. Okay, and there's a way to manually energize those if you had to. Okay, but normally that's not recommended. Now, the PLC is used in conjunction with a contactor to switch power on and off to a pump. Okay, here's your pump, there's your line 2, your L2 and L1. You're dealing with one side of the voltage for that pump. And then here's your PLC output module. Okay, and the PLC output module is providing the voltage to this side of the coil, and then you already got ground over here. Okay, so here you're using 24 volts to energize this coil that will power a 3-phase motor, possibly. Motor starters. Now these are basically the same thing, but these motors, I'll go back to that. There's one thing in this, the contactors, they don't have the overload circuits. You know, they may be turning lights on or some other big things like these big floodlights that they use at stadiums and stuff. That's possibly where they're using them, but I don't know. I would use something with some overload protection in it too. So these motor starters have the overload protection, and it's made up of a contactor with an overload relay. Okay, so you have the contactor with the overload relay attached physically to an electric to the device. Okay, they're usually little coils that heat up, and these things here, they show up in a ladder logic like this, and then it shows the motor relays. Okay, and once you energize the coil, again, this device, all these contacts will close once you energize that coil. And to do that, you hit this start button. Then you can release it. Well, one of the relays that are inside of here, other than those 3, is going to put this in a state where it's going to stay supplying motor voltage to that coil, which will in turn keep this motor running 3-phase. The only way to stop this is push that stop button. What that does is drops the voltage going through this relay here, and the coil on this device here will lose voltage, and it'll open these contacts, and this one will open also. So now, PLC programmed magnetic motor starter. This is what it looks like inside the PLC. Okay, physically you have these connections on the input side of your PLC, and then you have the motor connection, the voltage going out to that relay like we saw on the previous slide, and there's your L2. Okay, so what you do is you have your start button, and then you have the coil, the relay that goes with this coil, like we saw on the last diagram. Then there's your stop, and then your overload. Your overload relays are built in to your physical motor control starter. So, but they're in there just for explanation. Now, this is what it would look like on RS logic. Okay, this is what the program with the identification of everything, what it is, and so forth. Again, we'll be getting into that pretty soon. Next class or maybe next week. We'll start using the machines, I'm hoping. Now, manually operated switches. Now, these switches are push buttons, but they're normally closed, normally open, and this one's a dual, to what we call in electronics double throw. They call it a break make. You break one contact and make another. Okay, so essentially this one, this is a symbol. Uh, okay, and this one, when you open it, this one's normally closed. And there's a symbol for it, and that's a little button. So makes a circuit when it is pressed and returns it to the open position when the button is released. These are spring-loaded switches. Now, this one in the middle, it opens a circuit when it is pressed and returns it to the closed position. That's a normally closed switch. And this is when the button is pressed, the top end contacts open before the bottom end contacts are closed. So they just push down. Now, there are some of them, though, you press them down and then you got to pop them back. Okay? These here, I think, are spring-loaded. Now, a selector switch, you have 3 positions on the selector switch. Okay, and there's a little truth table. Okay, you've got contacts A are making right here, and in the off position, it's in the middle, so there's no contacts. And when you put it in auto, it's going to make the B contacts. So normally, this is normally closed right now in the hand position. In the off position, obviously, it's an open condition, and in auto, it's a closed position. That's the selector switch. Now, these are dual line packages. These are switches that are small assemblies. We've used those for years. They basically set you once when you configure a board or a device, and you don't mess with them much until you go troubleshooting it or you find something out. And normally they're a binary representation because usually there's 8 bits in there. So you can put a binary code in there. And there's a little register that reads those inputs and then it converts it to a digital signal and then goes from there. Dip switches are used in binary on and off settings to set the parameters for a PLC module. And that's cool. The DIP package, I wanted to mention this. I did. It's a dual inline package. The switches are inline and it has multiple switches. Now we have mechanically operated switches. These are limit switches, and you can see how they normally, there's a normally open in one condition and normally closed limit switch. Okay. And they're usually used to, like their name says, they limit an action. Like if you have something moving and you want to sense that it's moving too far, like an actuator or something, it'll release the voltage to a direction control solenoid, which controls a direction control valve in a hydraulic system, which will retract that actuator arm. And the limit switches will be used in a condition like that. Now, a temperature switch or a thermostat is used to sense temperature changes. Now, we have these kind of contacts. Now, this is a normally open temperature, and you can see it's got the little zigzag for temperature, and there's a normally closed, and this is normally opened. When it reaches the temperature that you preset it for, it will close on this one. It'll normally close when it reaches a temperature that you want, like an extreme high temperature or whatever you want to open it, or probably a low vent, because this one would be on the low side and this would be on the high side. Temperature switches open or close when the designated temperature is reached. Now, pressure switches are used to control pressures in liquids and gases. And here they show they have a little half circle at the end of a line that's hooked to to the contacts. They're just a symbol there. That's not what they physically look like. They're designed to open or close when they're contacts when a specific pressure is reached, and can be pneumatic or hydraulic, liquid, or any type of gas. You know. Now, level switches are used to sense liquid levels. They're used on sides of tanks, and they have a circle with that line there. And again, normally open, normally closed. When it reaches a level, it'll close if it's on the normally open side, and you know, if normally closed, will open when it reaches a certain level. So it depends on the way you put it in the system. Now we're going to talk about sensors. Now these sensors are proximity sensors are used to detect the presence of an object without any physical contact. And here's our representation of the proximity switch. And there's another company's version of it too, but this is what we use. Solid-state electronic devices are completely encapsulated. In other words, that means they're sealed up. You can't do anything to them. You just put them in a bracket and mount it. You adjust it for the distance that you need to get a good signal from whatever you're kind of trying to track with this proximity sensor. And it's an electronic device. It's not a pneumatic or fluid-driven device. Now, here is a proximity sensor. Now, they operate on different principles depending on the type of matter being detected. And now you have inductive, which the proximity sensors are used to detect both ferrous metals containing iron and non-ferrous metals such as copper, aluminum, and brass. Okay. There's an inductive proximity sensor operates with electromagnetic field, which varies in strength relative to a target. Okay, so if you put a piece of material over there, it'll get a higher voltage, which gives it a better signal, which will trigger something in the electronics. Now, the method of connecting a proximity switches varies with the type of sensor and its application. Now, you can have a 3-wire or 2-wire system. Most of the stuff we're talking about right now is just going to be 2-wire at this point. The load here keeps a little bit of voltage flowing through here to actually power the sensor so it can see something coming by. Okay, so if the sensor doesn't have any voltage on it, it's not going to measure anything if it's electronic. Now we'll get into one that's a reed switch or some magnetic something, and it won't care because it'll come on, it'll generate a magnetic field, and but if the sensors are LED or some sort of device like that, it needs a little bit of voltage. Now, most proximity sensors come equipped with an LED status indicator to verify the output switching action. So you can use that to help adjust it too, so you get the good signal when the light comes on. You know you got it positioned where you need it. Now, a small leakage current flows through the sensor even when the output is turned off. That's what I was just mentioning about that load. When the sensor is on, a small voltage drop is lost across its output terminal. To operate properly, a proximity sensor should be powered continuously. And then there's a bleeder resistor allows enough current for the sensor to operate, but not enough to turn on the input. Okay, the input into the PLC. Now, capacitive proximity sensors operate with an electrostatic field and are actually by both conductive and non-conductive materials. So it doesn't have to have metallic or ferrous metal in it. It can be a box. When the target nears the sensing surface, it enters the electromagnetic field of the electrodes and changes the capacitance of the oscillator, which gives you a different frequency, which you can convert into ones and zeros inside the PLC. Capacitive proximity switch sensors will sense metal objects as well as non-metallic materials such as paper, glass, liquids, and the larger the dielectric constant of a target, the easier it is for the capacitive sensor to detect. This makes possible the detection of materials inside non-metallic containers. Now, a magnetic reed switch is composed of 2 flat contact tabs that are sealed in a glass tube. And when a magnetic force is generated parallel to the reed switch, the reeds will be drawn together to actuate the circuit. Okay, and those are just little thin pieces of metal, and the magnetic force there closes them until that magnet moves. There's a magnetic reed float switch. There's your magnet, your float, and then there's the reed switch. As this float goes up, whatever fluid you have in there, it's going to close that. And see, the magnet will come up here and close these contacts. And this is your connector right here, where you plug in a connector. So this could be going into a tank, and when it reaches this level, it signals, okay, close this switch. So now the photovoltaic cell and the photoconductive cells are examples of light cells. Okay, now the solar cell, basically it produces the voltage when you have light and stuff, and it produces voltage. The other one actually changes resistance. The photoconductive cell, the one on the right. A photoelectric sensor operates by detecting a visible or invisible beam of light and responding to a change in the received light intensity. Now, photoelectric sensors are composed of a transmitter, which is your light source, and a receiver, and that's a sensor. Okay, that's going to sense the light. What you do is you bounce it off of something. You get to the next picture. So the scan-T refers to a method used by photoelectric sensors to detect an object. There, the through-beam scan technique places the transmitter and receiver in direct line with each other. Because the light beam travels in only one direction, through the beam scanning provides long-range sensing. Now, there is another one where you have one where it'll actually send out, and it'll reflect off of some mirror or something and then come back, and that way they use those for measuring distance. And in a retroflective scan technique, the transmitter and the receiver are housed in the same enclosure. That's what I was just talking about right here. And see, it's going to send it back. Okay, here's your transmitter and reflector, and it sends it back. Okay. Now, fiber optic sensors use a flexible cable. There's tiny conductors or fibers inside the channel. Okay, that channel light from the emitter to the receiver. Okay, in the old days we used to see this one here does it. It's got a transmission and a receiving, so it's going to bounce it back off the reflective. Now, barcode scanners are the eyes of a data collection system. The barcode module reading the barcode on boxes as they move through the conveyor. The one thing I have a hard time with, these boxes have to be placed wherever that scanner can see that. The PLC is programmed to divert the boxes to appropriate product lines according to their barcode. So, they'll have a little flapper over here to shut this path off going that way and send the box to your left. Once it knows, oh, well, that one's going to PA, and this one will eventually get to the truck that's going to or the truck that's going to go to Pennsylvania. This may be going to Ohio or something, so anyway. PLC is programmed, it's going to divert the boxes appropriate product lines according to the barcode data. So it knows by zip code or something. The post office does. An ultrasonic sensor operates by sending high-frequency sound waves towards the target and measuring the time it takes for that pulse to bounce back. So that's detecting the levels of chocolate or items, make sure that the bottles are full with material. And the returning echo signal is electronically converted to a 4 to 20 milliamp output, which applies a monitored measurement of level to an external control devices. So based on your output of that sensor, you're going to convert it to a voltage that's going to tell you, along with your program, is going to tell you how much material is inside that container. A strain gauge converts a mechanical strain into an electrical signal. Here you have a weight. The strain gauge, it actually measures the pressure applied to that object or whatever you're trying to use, and the force applied to the slowed cell causes it to bend. Thus, bending action also distorts the physical size of the cell, which in turn changes its resistance. When the resistance changes, you have a scale of resistance, and you convert that into pounds. A thermocouple is the most widely used temperature sensor. Thermocouples operate on the principle that when two dissimilar metals are joined, a predictable DC voltage will be generated. And that's essentially what happens. Those are used in your gas heaters, for your water heaters and your stoves. Of course, now they got electronic, your stoves all light up. They don't have a pilot anymore like they used to. Resistance temperature detectors, RTDs, operate on the fact that electrical resistance of materials is directly proportional to temperature. The hotter the RTD comes, the higher the value of its electrical resistance. Flow measurement involves converting the kinetic energy that the fluid has into some other measurable form. Inside of a flow meter, you have a little wheel that's turning and you're producing a voltage, okay, with an induction type sensor. Turbine flow meter use their rotational speed to indicate the flow velocity. Tachometer generators convert rotational speed into an analog voltage signal that can be used for control applications. So you can, if you have a variable speed motor, you can keep that motor running at a certain RPM, and that'll keep the line moving at a certain RPM or certain, RPM. But so that's what they use those for. It's a closed loop system. An encoder is used to convert linear or rotary motion into a binary signal. The optical encoder uses light source shining on an optical disc with lines or dot slots that interrupt the beam of light to an optical sensor. An electronic circuit counts the interruptions of the beam and generates the encoder's digital output. That's where you get a square wave, little pulses. And then output control devices. Now, these are your symbols for your output control devices. Okay, here we have a pilot light. Again, you got the little star thing around it. Now it's a control relay. It's a coil that you're energizing. Here you have a control relay, which you're also you have your normally open and normally closed contacts, and then you have a motor starter coil with your overload. Okay, and then there's an alarm. If you get voltage through that, you get an alarm. There's a horn. There's your motor. So you have a control relay that supplies voltage to the motor. And then you have a solenoid valve, which there's a solenoid and then the heater. Now, an actuator is a device that converts an electrical signal into mechanical movement. Electromechanical solenoid is an actuator that uses electrical energy to magnetically cause mechanical control action. Okay, so essentially, it's your coil is moving. The material is going to attract that arm to move to disconnect one set of those relays and make the other side contact them. Solenoid valves are electromechanical devices that work by passing electrical current through a coil to avoid changing the state of the valve. Okay, and here some symbols of it. Now, stepper motors rotate in discrete increments when electrical command pulses are applied to it in the proper sequence. Those motors, I don't know if you ever mess with those, but they just basically take a little bit of voltage to move, hundreds of thousands of an inch in increments. Depending on what the windings are set up in those motors. Every revolution is divided into a number of steps, and the motor must be sent a voltage pulse for each step. It may have 20 steps per one rotation. The amount of rotation is directly proportional to the number of pulses, and the speed of rotation is relative to the frequency of those pulses. The more pulses per minute, the faster that thing's going to turn. Servo motors operate in a closed loop mode, while stepper motors operate in open loop. There's no feedback system on a stepper motor. It knows that you send it that one pulse, it's going to move in that one incremented amount. Open loop is control without feedback. For the example, when the controller tells the stepper motor how many steps to move and how fast to move it, but does not verify where the motor is. Closed loop system, you always know where that motor is. Servo motor is operated in closed loop mode, and closed loop control compares speed or position feedback with the command speed or position, generates a modified command to make the error smaller. The error is the difference between the required speed or position and the actual speed and or position of the motor that you're controlling. Typical closed loop servo motor system is, you see that there where you have the controller, and then you have the load, and then you have a feedback device, and it tells you once the feedback device figures out maybe I need to slow it down or speed it up, it's going to send a signal to do that. Okay, so seal-in circuits. Now we've seen some of these already, so now we're going to put a name to it. A seal-in circuit is a method of maintaining current after a switch has been momentarily actuated. Okay, here's your seal circuit relay. Okay, this is your normal basic circuit that we've seen, where we have a motor control relay being controlled by a start button, energizing the coil in the motor control relay to pull and close these contacts right here, and also this contact here. So we hit the start button, and it provides the voltage to this coil, which closes these relays and this relay here. Once you leave go of that button, this motor is going to stay running. Now, if this relay had a problem and it didn't stay closed, the motor would stop automatically. And then the first thing I would check and make sure is you got good relays there, or the switch is not, the stop switch is opening sometimes. And the stop switch is how you stop the circuit, obviously. We've talked about that before. Programmed seal-in circuit. This is what it would look like in the PLC. You still have your stop button, and you have your start button, and then you have your seal-in relay, which is part of this coil, this relay system. Okay. Here we have a simulated seal-in circuit. Okay. Again, we have a stop button that's normally closed, and a start button that's normally open. And we have the motor starter coil was normally open. Okay, and these are not passing any voltage right now. Okay, they're examined if closed. Okay, and this one should be examined if opened. Okay, these are examined if closed. But anyway, normally what happens is this stop button is closed. As soon as you energize this button here, it's going to energize this relay, and then this relay will be closed. Okay, this switch will momentarily close and then open, and then this will, once you do that circuit, this guy is going to energize the coil, which is going to also close this relay here. And this is what it looks like in ladder logic symbols. And again, this is what you're doing in the plant. You're controlling the motor. Now, motor seal-in circuit implemented using the Allen Bradley Pico controller. Again, this is how the program looks in here. These are the physical contacts and the start and stop button. There's your L1 and L2 going into your input. And essentially what's happening is you have the Q1 right there. The motor's going to get loaded, turned on. Electrical interlocking circuits. Now, sequential hard-wired circuits. It's an electrical interlock circuit is used to prevent equipment or a piece of equipment from operating under certain potentially hazardous or undesirable conditions. Here we have motor stop, okay, push button motor 2 stop and motor 3 stop, okay. So what we have is we start this motor 1, okay, and motor 1 starts, and then you push the motor 2, okay, it's going to start, but you can only work if motor 1 is working. So if motor 1 coil is energized, this relay will be closed. But if this guy's not running, you can push this button all day long, nothing's going to happen. But once this coil energizes on this motor control relay, it's going to energize this and close this, okay? And then, so when you hit this button here, this motor will start, okay? And at that point, you can push this button once it gets up to the speed or whatever they're monitoring that. It's gonna, when this coil is energized, you're gonna close these contacts, which will give you the power when you hit this button to set the stamp, the circuit here to where M3 is energized. But that's kind of a sequence of operations. The only way you can start it is by pressing button 1. And then if you hit the emergency stop button, this button won't stop anything until this one is energized. Okay, so you start this guy, then you start this one, and then you start this one. Any one of these emergency stop buttons will only stop the one that the circuit's in until this one will stop everything, essentially. Because what happens is you stop the button here, it's going to turn this guy off, it's going to open this up, and this motor will stop running, which will open this up and stop this motor. And the programmed equivalent sequential control logic. That was essentially what I just explained, but this is what it looks like in the PLC, in the program. Okay, again, we still have our motor stop buttons, and we have our start buttons and our examine if closed here, along with this coil indicator here for a coil. Once this guy closes, this one closes, and this one over here closes. And once I press this start button or motor start button, this guy energizes, this one closes, this one closes. Over here, you got voltage coming down here, and motor 2, this one here closes, and then you got power to M3. Again, that's what it looks like in the PLC. And there is a better representation of it. That one back there was ladder logic. Yeah, that's ladder logic, but it's showing a little different with the PLC inside with the contacts on your I/O and input out, and then you see it in RS logic right here. Now, push button interlock is one of the methods of preventing two loads from being energized simultaneously. The hardware push button circuit is designed to prevent solenoids, solenoid A and solenoid B from being energized at the same time. So essentially, you hit right now solenoid A is being energized. Okay, you can de-energize A by hitting either one of these buttons. This hardwired push button circuit is designed to prevent solenoids A and B from being energized at the same time. Now this is the ladder logic version of it too. Okay, so you can see how that works. Now latching relays. Latching relays are basically when you power voltage to them, they'll stay in that condition. Electromagnetic latching relays are designed to hold the relay closed after the power has been removed from the coil. The latching coil is momentarily energized to set the latch and hold the relay in the latching position. The unlatching coil is momentarily energized to disengage the mechanical latch and return the relay to the unlatched position. This saves, some of these coils, if you got them energized for a long time, they can start getting hot. So these kind of devices are pretty good, but you have to have an on and off voltage going out to it. With a PLC, it makes it simple. The PLC output latch, which is the PLC code for is OTL, output latch, okay, and the output unlatch is OTU. So it's OTU for unlatch and OTL for latch, okay, and essentially OTL and the OTU instructions have the same address. The OTL instruction can only be turned a bit on, and the OTU instruction can only turn a bit off. So it unlatches or latches. 1 is a latch and 0 is an unlatch. Hardwired and programmed latching circuits. Okay, there's your hardwired we talked about before. Okay, and then there it is in the PLC, and there's just pins that it's on. It's on, output 2, pin 5. Okay, and so whichever input hits it is going to either latch it or unlatch it. It's going to change that bit from a 0 to a 1. If it goes to unlatch, it's going to change it to a 0. And if it's going to latch it, it makes it a 1. And then the PLC takes that and sends it to some output to de-energize this circuit or energize it, depending on the condition of this latch circuit is going to either turn this light on or turn it off. And there is a PLC version. See, it's off and on. Then the unlatch is off, latch is on. You see where that is? It's still 025, but it's the latch side of the circuit. And you'll see a box with the latch in the PLC. We'll get into that. Process is used to control the level of the water tank and the storage tank. Okay. Here there's a manual mode. The pump will start if the water level in the tank is at any level except low. Okay. Now in automatic mode, when the level of the water reaches the high point, the pump will start. When the water level reaches the low point, the pump will stop. And then you have the lights, pump running, low level and high level based on these sensors. Now here's the circuit. Okay, you got a manual, auto, you got an on off, you got the low sensor switch and the high sensor switch. The high sensor is going to possibly turn the pump off because it's going to stop putting fluid in the tank. And the low sensor will energize the pump. And then here's the logic for it. Okay, the ladder logic side of it. Okay. Now connections for the program. Now this is essentially the same program. You have the motor, you have a pump running, it's your motor relay, and the low and the high level light. Okay, and these are the output pins, 1, 2, and so essentially these are your input pins, and your switch is off, and this is your L2, and then your manual mode. Okay, it's open. Auto, it stays closed. And then the low sensor and the high sensor. The manual mode is going to turn the pump on. Okay, now the sensors will control the pump action once you set it to auto. Okay, the manual, just use that switch up there to turn it on and off. Now, the simulated action of a program used to control the water level. The B is manual, A is auto. we're going to converting relay schematics into PLC ladder diagrams. Converting relay schematics into PLC ladder programs. Now, a sequential control process is required for processes that demand that certain operations be performed in a specific order. In a filling and capping operation, the tasks are fill the bottle, press on the cap. The tasks must be performed in the proper order. A combination of controls required that certain operations be performed without regard to in the order to which they are performed. Here is the task, place the label on a bottle, and 2 places label 2 on the bottle. The order in which the tasks are performed does not really matter as long as you get both labels on the bottle. And automatic control involves maintaining the desired set point at an output. When maintaining a certain set point temperature in a furnace, if there is a deviation from that set point, an error is determined by comparing the output against the set point and using this error to make a correction. Now, sequential process is controlled by relay schematic. Now here we have the start button is pressed, okay, and that's this guy right here, okay. The table motor is started. This relay goes, and control relay starts that motor. The package moves to the position of the limit switch, and automatically stops. It's essentially what the process is. Now, this is what the sequence process in the control program. Okay, this is what your PLC would look like. And here you have the I/O addresses of the devices, and you see which one. There's your motor, and which you're controlling it with. There's your limit switch, which is I32, which is, I thought it would be right there. It's right here. Okay, it's going to stop right there for the motor. So these are hooked in series. Okay, so these two have to be made for this guy to work. So either one of these, which is push button 2, which is your stop button, and your limit switch is going to drop the voltage to this, which will drop the voltage here. This is your start button here. And then this is your sequence process control program, simulation, and RS logic. And we'll probably write something like this, and we'll be able to hit the buttons on the left side and see what happens to the light on the right. Now, instruction program for optimum scan time. This series instructions are programmed from the most likely to be false to the least likely to be false. Okay, and the parallel path that is the most often true is placed on the top rung. Okay, and then you go down the line. Hardwired jog circuit. Now, in the jogging circuit is where you can push a button or slide a little lever and put power onto either a motor or something that you're trying to control to get it to move just a small distance, okay, rather than just turning that switch on and having the juice to the motor all the time. Could be positioning an arm on a robot arm or something like that, and usually you use a control relay for that. This is really how a ladder diagram writes. And this is, you have your voltages, you take some tap off of it, and then this is your overload circuit on your motor. This is your control relay. This is your motor, and then this is your jog button. So essentially, this is wired a little differently, but it's still, once your control relay gets energized, CR1 energizes, which keeps everything running. And then you hit the jog button right here, and you can keep even without the control relay 1 running, you can still energize the motor. Okay, and CR2, and then your motor relay here will keep the jog to where you got able to use it. Okay, because CR2 will be in here. Now, equivalent programming for the jog circuit in a PLC. Okay, you have your start, your stop, and then your relay right here. From your solenoid being activated, it's going to start the circuit here, and then these situations will stop it. Okay, the jog will let you. The jog will let you run this way, and the stop, it's going to be closed. If you hit the stop, you can't jog it. Okay, there's your motor over there with its output location on the pin on the output module. And this is your NRS logic, what it looks like. Now, writing a ladder logic program directly from a narrative description. Drilling process requires the drill press to turn on only if there is a part present and the operator has one hand on each of the start switches. Okay, so here's your 2 push button sensors, and then here's your sensor. Now, normally it'll be a sensor to say the drill press is only turned on if there is a part present. So that switch has to close. When there's no part there, it's open. Okay, so essentially, as long as it's your push button 1 and 2 have to be closed, and your sensor have to be closed in order for this circuit to energize the contactor, which will energize your motor. Okay, so he's got his both hands on the buttons, and there's a part in there. And then here's the ladder logic simulation, even though it's got the screen up there. We know we got that there and those there to get a little fancy here. And a motorized overhead garage door is to be operated automatically to protect the preset open and closed positions. There you have the upper and lower limit switches, and it will, as long as the upper switch is closed, the lower lit switch, you can move your door up, and once it hits that upper limit switch, it de-energizes the motor. And this would be what you're looking at here. Okay, and then you have the lights here to tell you whether the door is closed, the door is open, the door is ajar. In other words, it didn't shut all the way down. And there's your up and down motors. And then over here you have your 2 switches. Your upper limit and down limit, and door up button, door down button, and then stop button, so you can stop it anywhere you want. Now, a simulated motorized overhead garage door program, this is what it looks like in RS Logic. Okay. Now, you want to continuous filling operation. This process requires that boxes moving on a conveyor be automatically positioned and filled. Okay, so there's you got a run, standby, and a full. There's your photo switch, your motor, your start stop button. These are your physical, and this is your solenoid so you're going to fill that box up to a certain level, and this solenoid is going to be energized or de-energized. And if it's de-energized, it's going to open up the flow of the material from the hopper to the level, and then this level switch is going to detect it. So you have to write the logic for that. And here it is. The photo cell, the lever, level switch, and then your start and stop button. And then you have your full, standby, run, solenoid, and the motor. Solenoid is going to be the energized for closing or opening the flute, the flow of the fluid. So here you have the box with the sensor, and then your solenoid over here. This is your circuit. Instrumentation. Instrumentation is the use of measuring instruments to monitor and control a process. It involves the design and calibration of systems used to measure, record, and control industrial process variables. And these variables may include the pressure, temperature, flow rate, weight, and chemical consistency. So you can measure a lot of things with these devices. Each instrument has at least one output and one input. Okay, you got pressure input and you have a voltage in milliamps or output. For a pressure sensor, the input could be some fluid. For a pressure sensor, the input could be some fluid pressure, and the output could be 4 to 20 milliamp current signal. Smart instruments that contain microprocessors have built-in diagnostic ability, greater accuracy, and the ability to communicate digitally with the host devices for reporting of various parameters. These are becoming, they're going to be more intelligent devices out there that'll send a lot more data to the PLC. The PLC's role. The PLC's role as a part of the industrial instrumentation system is to receive, process, and send signals from input to output devices. With the use of programming software, the PLC can control, monitor, and display all the parameters associated with a given process. I think that was the last slide. So anyway, after you finish this, you can go to, there'll be a Chapter 6 quiz under Blackboard, and I need you to finish that before the end of the week, which is Sunday, the end of this week, because I need it done so that way I can get that you were attended, and that you actually read the chapter. So this grade will be a participation grade, so it'll go towards your participation points. So I want you to try and do the best you can on the quiz, and good luck. Thanks.